Alright, so far we've named binary compounds. Binary literally means two, either or, one or two, 0, 1. That's usually how the computer language works. Alright, so there are a couple rules we talked about. One is if it's a salt. So if we have a salt, that means we have a nonmetal, usually plus a metal. But in particular, we have an anion plus a cation. And the negative is the anion, cation is positive. In general, when you name these, you're going to name it with the cation first, followed by the anion, and then we're going to have some suffix on here, depending on what we're looking at here. I just want to point out here that it's not always a metal and a nonmetal. We do have some examples where we have all nonmetals, and ammonium is the most common example. Alright, so we had a few examples such as sodium chloride, for elements with variable charge, you must denote the charge by using a Roman numeral. Common example here are things that are in the transition metals. That's not always the case. I did give you some other exceptions here on this table. So these are the nomenclature rules that are online. Notice right here I give some exceptions. The main ones that I want you to be aware of in this group here are tin and lead. They can be either a +2 or a +4. Alright, so let's go ahead and do an example with the name, and then we get the formula from it. So lead, I said lead can commonly be a charge of 4. We put that in parentheses. And then here, let's go ahead and say lead 4 sulfide. So from this, we can go ahead and figure out what the formula is, because we're being told what the cation is. Oops, 4 plus. And then sulfide is S. This one has a common charge of a 2 minus. Alright, we can now do the cross method to figure out what we have here. But you need to be careful here because we're not actually going to get the correct answer this way. We're going to get a close to the correct answer. So by following this here, we end up with Pb2S4. Notice here they have a common multiple of 2. So the way to properly write this formula is PbS2. You need to have the smallest whole number ratio between the elements if you're dealing with an ionic compound. This is not true if it's molecular. Alright, the other naming that we went through that was binary compounds were acids. So we had binary acids. There are technically three different definitions for acids out there. The one we're going to go with is something that is an acid is something that donates an H+ ion. The way we denote acids in their formulas is we write the H first. And this is also consistent with the way we've been writing formulas previously in that we write the cation first and then the anion. So in this case, in an acid, your H+ is going to be your cation. The binary acid is hydro, your element name, ic, space, acid. And I do believe the example we did last time was HCl. And this is hydrochloric acid. I did want to point out most of these binary acids are going to be halogen that they're paired with. That's going to be the most common way you're going to see it. So let's do another one, HF. So what should I call this? Hydrofluoric, yep. Hydro, and be careful on the The spelling of fluorine is F-L-U-O-R. Particularly nasty stuff, that hydrofluoric acid is very toxic. And if you ever see it stored in the lab or in a stockroom of some sort, they will not store it in glass. It'll be stored in plastic because hydrofluoric acid will actually eat through glass. And then eventually, over time, your glass bottle will just fall apart. So we use plastic instead. For some reason, it does not touch plastic at all. So it's random trivia for you guys. All right, the last type of binary compounds we did not name yet were if it's molecular. Molecular compounds in general is when you have all nonmetals. These do not form ions. All right, the general way to name these are that we use the element name with the prefix. So prefix, and then we'll have a first element. We will have a space, and then we will have another prefix, and then you're going to have your second element, and then we give it the IDE ending. These prefixes are for how many of that atom there are, because remember that these don't form ions, so we're not going to be able to use the name to figure out what charges are to get the formula, so that way you need to tell the reader exactly how many of that atom you have. Because we can't basically do that same thing we were doing before where we figure out what the charges were, work backwards. We can't do that here. So your prefixes here equals number of atoms. So I want you guys to be aware of prefixes for 1 through 10, just like we have with the Roman numerals. So let's just go ahead and make a list here. You're going to see these types of numbering all throughout your science courses. They're very, very common to use these for numbering. Here, let's go ahead and name this one. So notice here we have 1. You might think that it's going to get the mono prefix, but usually what happens with this is if you only have one of the first element, we drop the mono on it. So we just call this, so what is that, potassium? It's phosphorus. And then we need to specify how many of the fluorines there are. So trifluoride. Remember, once again, with the molecular compounds, you have to use the prefixes on there because we don't have charges to work with. All right, the next one here, we have 2 of the bromines. So dibromine, 3 oxygens. So we actually abbreviate oxygen quite a bit. We just use the OX for that. So trioxide. I did want to mention in the case of where you have only 1 oxygen here, usually one of the O's is dropped. So you don't say monooxide, you would say monoxide. Just roll it all into one word. So a common example for that would be what, carbon monoxide, right? Which was, just go ahead and put this down here. CO. This would be carbon monoxide. So we don't call it monooxide, we just say monoxide. And then CO2, carbon dioxide. And then H2O, well, what would that be? Dihydrogen monoxide? I've seen a lot of people calling water dihydrogen monoxide at places like Facebook, and they're basically making fun of all this GMO craze going on. They'll say, oh no, it requires dihydrogen monoxide. It just sounds toxic when you say it that way, but it's just water. All right, let's go ahead and just finish up this here. So chlorine, we only have 1, and then dioxide. This next one here, Si, what element is that? That's silicon. And then what should I call this last part, do you think? Tetrahydride. So tetra for 4. So hydrogen, we just abbreviate that as hydride for short. All right, the last one here, we have 4 phosphorus. So tetraphosphorus. And then what prefix should I use for the oxygen? Yep, so decaoxide. Only drop the vowel if you are working with mono. Honestly though, if you wrote decaoxide, I wouldn't mark you off, but people do that all the time. Because the double vowel makes it kind of awkward. Alright, we did talk about this a little bit last time. Recall that poly means many, so we have many atom ions. So that's where your poly comes in here. There are some common ones, and I noticed the way your book is reading, it's basically telling you to memorize all this stuff. And there actually is a systematic way to name the different polyatomic ions. There are some that you have to memorize because they're oddballs, but there are a lot of them that have a common scheme to them. So I do want to mention here that many of the polyatomic ions are oxyanions. And that's just as you may think. It is anions that have oxygen in them. Alright, so let's go ahead and take a look here. I think the best example here would be to look at chlorate. So notice here I called this one chlorate. Whichever one is your base oxyanion, we'll go over what the base means here. It basically means that's your standard number of oxygens. We give this the ATE ending. The other possibilities are named in respect to this one. So if you have an extra oxygen compared to the base name, so we're going to say it's +1, so that's ClO4, we give it the same charge. We use the per prefix ATE suffix. So this is perchlorate. When you are naming them, you basically just use these names for your anion names. So instead of chloride, you say something like chlorate or perchlorate, etc. This is our base right here. So we can then have a -1, a -2, and then a -3. Alright, so if you're -1 compared to the base one, we give it an ITE ending. So we call this chlorite. So how many oxygens should I have? 2. And same charge. Alright, and then if you are -2, we give this the hypo prefix and the ITE ending. So this is hypochlorite. And we have ClO-. Alright, in many of the cases, if you have this here, -3, that typically means you're at no oxygens at that point. And we just give it the standard IDE ending that we've seen before. So this next one here is a Cl-. This is chloride. Alright. So in naming all of the halogen polyatomic ions, they're going to follow the same scheme. So this next one here, what would you call that particular oxyanion? Bromite, yeah. Alright, and then if we had IO4-, what do you think we should call that one? So comparing it to the chlorine, we should have per-iodate. Yep, per-iodate. I did want to mention, in general, in chemistry, we like to use the per prefix to basically denote extra oxygens. So you may have heard of something like hydrogen peroxide. It's basically telling us that it's water with an extra oxygen in it. So it's H2O2 instead of H2O for hydrogen peroxide. But that's what the per prefix is. Very common to see that in chemistry. All right, so let's go ahead and take a look at an example. So NaClO, we can now name this. So we name the first part exactly the same, sodium. Do I need to tell the reader what the charge is on sodium? Nope, it is a main group element. It's in the first column. And then what should I call this part? The ClO. Hypochlorite, yep. And then in your everyday lives, people like to call this bleach. This is the common name. So if you grab your bottle of Clorox bleach, I know it has it on Clorox, I'm not sure about the other brands, but in the really tiny, tiny font in the bottom, it'll say 5% sodium hypochlorite on the bottle. Usually it's really, really tiny font, like 6 font on that huge label, right? But it's really tiny in the bottom. I've seen it on there. I know Clorox has it. I'm not sure about the others. All right. So that's pretty much it for the naming on these. The hard part usually is figuring out what the base is, because the base is not always 3 oxygens. Sometimes it's more, sometimes it's less. Usually it's more, though. All right, so let's take a look at an example. So for example, PO4 3-, I would not name that as a perphosphate. That is simply phosphate. So notice here the difference is there are 4 oxygens in the base name, or base ATE ion. So there is actually a very easy way to remember which ones have 4, which ones have 3. And it's a really silly mnemonic here, but it works. So if you take a look at the periodic table, and there are 5 elements here that make a 4 shape. So I'm going to outline the ones here, and notice the shape they're going to make. It's going to look like a number 4. So we have phosphorus, sulfur, arsenic, selenium, tellurium. These all have 4 oxygens in their base ATE ion. The main ones you're going to run across are phosphate and sulfate. So let's just go ahead and take a look here. Phosphite is not very common, but you're going to see sulfate, and then you're going to see sulfite. Every other one, they're going to be on the outside here, so carbon over, not including oxygen, of course, and then the halogens, those are all going to have 3. So let me go ahead and write it here. So these have 4 oxygens in their base, and then these ones all have 3 oxygens, and it goes all the way over here and then down. So let's go ahead and use a name here, or let's take a look at calcium phosphate. So we have the name, I want to get a formula. So calcium is a common one. Main group element, it is in the second column, it is Ca2+. And then the next one here I just gave you up here. Alright, we can then do the cross method to figure out how many of each we need. And when you're working with these polyatomics and you need more than one, you need to make sure you use parentheses, right? So I need 3 calciums. I'm going to put the phosphate ion in parentheses, and then a 2 on the outside. saying that I need 2 phosphates to balance out the calciums here. I cannot reduce that any further. So, for those of you who've taken some biology classes, where does calcium phosphate occur in our bodies? It's in your bones, yep. Your bones have a very high concentration of calcium phosphate in them. You guys will do an experiment in Chemistry 121 where you'll make calcium phosphate, and you'll notice that it's not soluble in water, which is actually a very good thing, because if our bones were soluble in water, that means it would be a big blob rolling around, because it would dissolve in our blood. So, not a good idea. All right, let's take a look at a couple more examples. So, let's say we have iron 3 sulfate. Alright, just like before, we have an ionic compound. You want to use that name to get your charges. So Fe3 plus and SO4 2 minus. And using the cross method, we're actually end up with a very similar case to what we saw with the calcium phosphate. So we need 2 irons. Since we need more than one of these, we have to put it in parentheses and then drop the number 3 afterward, like so. And then check if it can be reduced further. That cannot be reduced any further, so we're good. Alright, so not all of your polyatomic ions are oxyanions, and there are some common ones that I want you guys to be aware of, and they are on this handout here. And let me just go ahead and list them here so we have them in our notes. I have listed chromate and dichromate. On this sheet, there is a typo in the charges. The charges should be 2 minus on both of them. So to keep that in mind, that on chromate and dichromate, the charges are 2 minus. So let's take a look at using some of these examples. Honestly, you're going to commonly see the sodiums and potassiums paired with permanganate and chromates. That's really common. So the most common form of permanganate you're going to see is KMnO4. So what is that, Kalium for K? Is that what that is? That's actually the old name for potassium. That's where the K comes from. But this is potassium permanganate. You use that whole thing as the name. Potassium cyanide. So same fashion here. Potassium cyanide is actually the common form of cyanide that's out there. And rumor has it smells like almonds. So by the time you can smell the almonds, you're probably passed out from it. So I'm not sure how people know that. Alright, let's go ahead and combine a couple of these. You may see some combinations of NH4 with other ones. So the very common one you may run across is NH4OH. Very common. So the cation is ammonium. Yep, ammonium hydroxide. So when you guys clean your windows with Windex, what are you guys cleaning your windows with chemically? You guys know? Ammonia. It's ammonia. It turns out if ammonia by itself is actually a gas at room temperature, but that gas is actually very soluble in water, and it turns out that when you have ammonia in water, it's technically ammonium hydroxide. But people will often refer to this simply as ammonia for short. Na2Cr2O7. So we have sodium, And then we have, what? Dichromate. You can remember this is the dichromate because we have 2 of the chromiums in that ion, right? All right, let's just do one more while we're at it. So Mg C2H3O2 close parenthesis 2. So what anion is that I drew there? Acetate. So magnesium acetate. Alright, so bear with me guys, we're almost done with this nomenclature stuff. So naming polyatomic acids. So in general, acids are what? Things that produce H+, right? So in naming them, we don't name them after the H+, because we already know it's going to have H+, it's an acid. The way you name acids are from their anion. So we already went over the binary acids. We had the hydrochloric, hydrobromic, hydroiodic acids. So now we have to deal with the fact, what if the anion is polyatomic? So there is a general scheme for this. So let's go ahead and just use the chlorine example again. So we had ClO3 as our base. And we call this what? Chlorate, right? It turns out that if you have the base number of oxygens, you just drop the ATE and say ic acid. So it's chloric acid. Don't put the hydro in front. Hydro denotes that you have a binary acid. So if you have oxygens, we don't put hydro in front. And we just call this one chloric acid. Alright, we're going to have a similar setup here. So with the naming here, if we have an extra oxygen, this became perchlorate. And then we have HClO4. So if we're following the same scheme here, what do you guys think we should call it? Just perchloric, right? So notice the difference here. We just had a per prefix here. So perchloric acid. All right, and then if we have one less, this is where we have chlorite. And the corresponding acid would be HClO2. So instead of the ic acid, we're going to use OUS acid, chlorous acid. OUS acid. And let me just go ahead and highlight what's happening here with the naming. So per ic acid, and then us acid. All right, and then next one here. Here we had hypo. For one less, it's still a chlorite, so hypochlorite. And then we get HClO, so hypochlorous acid. And then the last one here, we had Cl minus, no oxygens, we called this chloride. And this became HCl. So this is when you use the hydro, when you have no oxygens. It's basically to separate it from the other name up here of chloric acid. All right. So with that in mind, let's just go ahead and do some examples. When you're doing the namings here, remember they're always named after the anion, so identify what the anion is first, and then get the name from there. So for example, I want to go ahead and take a look at sulfuric acid. commonly called battery acid. You may recall on the periodic table that I showed you guys, if I can find mine. How many oxygen should I have here? Sulfur is one of the ones that is outside that 4 shape, so it's 4. And sulfate has 2 minus. And we know the cation is going to be an H plus because it's an acid. It says so in the name. So how many hydrogens should I have in the formula? H2SO4. It's a shame we don't have a lab because the reaction with sulfuric acid and table sugar is kind of cool to watch. But if you have me for a lab next semester, you'll see it. All right, so sulfuric acid. Let's go ahead and take a look at some other examples. So what about, let's do it the other way this time. HC2H3O2. So breaking this apart, I notice that we have an H plus as our cation. And then what anion is that? It's acetate. So yes, it's not quite the same, but we're going to use the same scheme as before. It has an ATE ending. So ATE ending gives you ic acid. So what do you think we should call this one? So if it's acetate, acetic. Yep, acetic acid. Does anybody by chance know the common name for acetic acid? You very likely have some in your kitchen. Very, very likely. If you make sweet and sour sauce, it's the sour part that helps. It's vinegar, yes. Yeah. For those that didn't know that, this is the sour part of sweet and sour. The sweet part's brown sugar. Very easy to make. Takes 5 minutes. But people spend all kinds of money on it in the grocery store. All right, let's go ahead and take a look at some more examples here. Just keep cranking through them here. So what if we have H plus and CO3 2 minus? What do we call that? So here we have 3 oxygens. It's not one of the ones that is part of that 4. So that is the base name. So it's carbonate. So this is carbonate. So what do you guys think we should call the acid form? Carbonic acid. And this, putting this together, is H2CO3. And I do want to mention here that I have talked about water and CO2 mixing and how it makes it acidic. This is actually what happens when water and CO2 mix. We'll go into more detail with that later on. I just wanted to point this out here, that is the acid that forms when you mix CO2 and water. It becomes carbonic acid. So when you guys drink your soda, you're probably drinking a mixture of carbonic acid, and they usually add phosphoric acid in there too. So with that in mind, what is phosphoric acid? So we need to always recognize that we have an H plus as our cation, and then should this be from phosphate or phosphite? Which one should it be? It's ic acid, so it came from phosphate. So now we need to figure out what phosphate is. Yep, PO4, and then what's the charge? We did this one earlier today. 3 minus. All right, and then putting everything together, we need 3 of the hydrogens to balance out the phosphate. So H3PO4 for that one. right. So we actually are done with all the names. Yes. Yeah, make sure that you guys do a ton of practice with these. That is the only way to learn it, is to do a bunch of practice. There is one little subset that we did not talk about yet, and that's if you have these ones that have a charge that's greater than 1. So like your -2s, -3s. Sometimes you may see them paired with an H, but they don't have enough H's to make it neutral. So let's take a look at an example. So here we have, this is the most common one you're going to see. This is carbonate. And if we pair this with an H+, so just one H+, what do you think the charge should be now? Should it be -2 still? Or should we raise it by 1? What should we do here? What should the charge be? We have an H+ and a CO3 2-. Adding those together, it's overall -1. If we had it fully balanced and neutral, that's what it would be. This here is a common anion you may see. There are 2 ways to name this. The harder way would be hydrogen carbonate. The common name that you're going to see that I would prefer that you guys use is bicarbonate. So we put Bi in front, so bicarbonate. Alright, so an example would be NaHCO3. This is sodium. You can call it hydrogen carbonate or bicarbonate. Another common household chemical. Does anybody know the common name for sodium bicarbonate? Yep, it's baking soda. So you guys ever seen the reaction if you mix vinegar and baking soda? I did that earlier when I put out the candle with the CO2, it generates CO2 gas. So, but that's for a later chapter. All right, so that's pretty much all that I have for you guys today.